everyone. I'm Roma, and today we're going to be presenting grounding language to non-Markovian tasks with no supervision of task specifications. This is joint work with Ellie, Pavlick, and Stefanie, Tellex, both at Brown. So let's look at an example scenario that motivates what we're doing. You can imagine an instance where a robot is in a house, and you want it to move to another part of the house to perform some task, and you would like to speak to it in the way that you normally do, which is in natural language. And maybe when you're teaching the robot how to do these tasks, the easiest way is to give it a demonstration of what it means to solve this task. And then internally, what the robot has to do is to turn each of these natural language instructions into a program or some kind of symbolic logical form that can be executed to the demonstration that you just showed it in the real world. And we also want to ground to a more complex logical form that can allow handling of temporal constraints during planning, which is why we're going to use linear temporal logic. Now, any kind of model that attempts to do this has two main components: a generative model that produces a set of logical forms that you want to score, and then a supervision or a model checker that tells you whether or not the logical forms that the model produced are correct with respect to the task at hand. Now, for the generative model, we draw from previous work by Gu and Liang and Goldman and Birant, where they create these weakly supervised beam search algorithms that are optimized using reinforcement learning to get feedback from executing a logical form, for example, querying a database or taking an action in some toy world, instead of the usual methods of actually comparing whether or not each of the tokens generated were correct. And in our case, we need to learn to get feedback when our language is in the form of LTL. And how we're going to do this is with LTL progression. So we're going to make use of the fact that the rich semantics of LTL operators allow us to define these progression functions. So for example, I can take in my state of the world, sigma I, and the current LTL expression, and progress the expression based on that state. And a simple example is if my proposition P in my LTL expression in the top left corner referred to a red chair, and my state sigma I did contain a red chair, I can evaluate to true for the first part of the expression, and if not false, and so on. And in this way, when my generative model produces an LTL logical form that it needs supervision for, I can progress it against a trajectory to evaluate a true or a false, which is a +1 or a 0 reward. And then finally, in order to get large amounts of data to train this model, we're going to algorithmically simulate trajectories in real-world environments by creating connecting graphs in environments, randomly sampling start and end nodes in these connecting graphs, and then running variants of shortest path algorithms, for example, the kth shortest path algorithm, to get trajectories, which are then annotated by humans. For example, on the right, you can see that we have trajectories for different maps in real-world environments based on the simulator trajectories that we generated algorithmically. And it's worth noting that this is really the only place where we've needed humans to come into the picture. And we're still only asking them to annotate trajectories with natural language and not anything that's more complex like LTL. But we're making use of all of these algorithms and LTL progression and model checkers to allow just this minimal amount of supervision to be enough. And now let's look at evaluation and whether or not it really is enough. So the first set of results is over SAIL, which is an artificial grid world environment that is quite complex in the variability of natural language, but it doesn't really call for the use of temporal constraints. We can see that our model, which is the last row, has comparable performance to the best performing model, but the seek-to-seek, which is me et al. In the second last row, outperforms it over all instructions when you measure goal state accuracy. But then when we look at the subset of instructions in the bottom row, which says temporal instructions that actually contain temporal constraints, we can see that our model actually outperforms the seek-to-seek, which is nice to see. And then when we evaluate on the newly collected data, which is the more complex temporal constraints in real-world OpenStreetMap environments, we can see that our model outperforms the baseline in nearly all of the environments. And finally, we do a demonstration with the Skydio drone in simulation. So we do this over 6 different real-world OpenStreetMap environments for unseen natural language commands. And we can see from the video that it actually follows the commands correctly. Thank you, and here is the video.